Fantastic. I'm excited to be in home. Not Mountain View is not my home. San Jose is home, but I've been in the Bay Area for 20 years. It's exciting to be speaking in the home. Fantastic. Yeah, so my name is Arun Gupta. I'm a principal open source technologist at Amazon. Been with them for about 2.5 years. Thank you for the kind introduction, John. And I've really enjoyed being at all of the community days. That's one of the things I do at AWS. I engage with communities worldwide, talk to customers, understand what their pain points are, and we always innovate on their behalf. So today I thought we'll talk about a topic that is something very close to my heart. How many of you like to get up at 2 in the morning when you get a system call that your system is down? Anybody? Right, isn't it? So let's talk about how we can, fix that problem. So how can we introduce chaos and make your systems more resilient? So this is Werner Vogels, his CTO for Amazon.com. He wrote this article, and the link is at the bottom, on the 10th anniversary of AWS. And he talked about that how failures are given and everything will eventually fail over time. Whether you buy the most expensive hardware, whether you buy cheap sockets, whatever you want to buy, whatever you are running will eventually fail. Your memory would crash, your packets would get lost, your hard disk would crash, your network connections would be broken. Things are going to break. And particularly at Amazon scale, think about S3. S3 is processing trillions of requests per day. Anything that could potentially break would break over there. So something that we have learned over several years of execution is how, if things break, how we can confine the blast radius so that the impact is not big. And we always think in terms of how can we cut down the blast radius and how can we minimize the impact, not just to customers, but to internal services as well. What is this number? Any guesses? Shout out.
The number of Amazon releases that come from customer requests.
Oh, that's Corey. All right, Corey. Well, I didn't realize Corey is here, so now you're here. All right, no worries. Well, this is the number from a 2014 paper from Usenix. And it says, basically what this means is, the 92% of catastrophic failures can be prevented by handling your non-fatal errors that are showing clear symptoms in your code. So if you can handle that, imagine if you can reduce this many amount of catastrophic failures in your system. That is a huge number. It's a huge number. So let's talk about what is sort of chaos engineering. Let's talk about what is the background of chaos engineering and what it brings to you. Chaos engineering, we started back in 2006. So Jesse Robbins, founding CEO of Chef, he started doing game days. And the whole concept of game days was around operational excellence. So security is job zero at Amazon, followed closely by operational excellence. So he started doing these game days, and essentially the idea is he'll go into the data center and start pulling things down, start shutting services down, and see if the services are resilient. We do game days before a major region launch. We do game days before Amazon Prime days, which was just happened in July. So anytime there is a major thing going on that is going to be released to the customer, few days, weeks before that, we run a game day and simulate what if the customer spike goes high? Like lots of customers are, sending it. What is the SLA and things like that? We simulate the environment because that is what happens in the real world. In 2010, Netflix started, talking about Chaos Monkey. They released this tool which can randomly terminate, virtual machine instances. So Chaos Monkey was built with the virtual machine idea. There were no containers at that point of time. So it would randomly go terminate VM instances. Now it has been adapted to use containers as well. So it will randomly terminate containers, yet making sure that your applications continue to behave. And that's where you identify where your application is breaking apart. Is it resilient? Is it going to be able to scale? And things like that. Netflix built a much more comprehensive tool suite around that called a Simian Army. They released that in 2012. Gremlin. Some of the engineers from Netflix left and found a company called Gremlin. Colton particularly is the founder of Gremlin. I had a dinner with him over the weekend, so that was really cool. Actually, earlier this week itself, there's a book around chaos engineering that some of the Netflix engineers wrote. So I'll talk about that briefly. And now we are seeing it's becoming more and more mainstream. As a matter of fact, the third version of Chaos Conf is happening on September 27th. So if you are in the Bay Area, this is happening in San Francisco. And when I was talking to Colton, he was telling me that for the first two conferences, it was more about awareness. For the third one, they're really talking about how. That's what customers want to learn more and more. That, okay, I understand the concepts. Tell me, how do we implement it? So let's talk about resilience for a second. We have all fallen sick some point in the time. And guess what? We all have recovered well. So there are a few lessons that we can learn from the Almighty, that how He has built our body. We fall sick, we have a fever, we break something, but then we go through the process of recovering. That's what resilience is about. Now, bring that analogy into software and see how you can react, you can make your software react to changes, failures, and disturbances in the system. And those changes are real-world events. It could be, all of a sudden, I tested my software for 100 concurrent users. Now the app is popular, I'm getting 100,000 concurrent users. How that's going to work? Vertical scaling, horizontal scaling, lots and lots of concepts that go around this. So let's get the definition of what chaos engineering is. I'm going to read the definition for you. It's a discipline of experimenting on a distributed system in order to build confidence in the system's capability to withstand turbulent conditions in production. Let me highlight a few parts here. The production part is the really key part here. What that means is you are not doing this in a dev or a test environment. There is no urgency if you're doing it in a dev and test. Things fail, it's okay, we'll recover. You do these things in production, because then there is an urgency, then there is a rush that the customer is not being served. The other part is, you define experiments, that what those experiments are going to do. And you don't blast your entire customer base with that. You really control the scope of the experiment and who you're going to target. So that's the experiment. And the whole idea for this is really to build confidence that, okay, if these experiments were to happen in real life, how this is going to work for me. Is my application, is my system going to behave? Is it going to be resilient? Is it going to be able to recover? So how do you apply chaos engineering? What you do is you break your systems on purpose. You identify, I'm not talking about unit testing, functional testing, integration testing. That's done by your usual CI. But what you do is you look at the conditions that you would not think in terms of usual testing, but you really break it on purpose. What if, 2 o'clock my service goes down in the morning? How does it behave? What is my experience in there? And I'll share some examples of that personally. But that's sort of the idea. But you might think, dude, this is scary. You're asking me to break the systems on purpose. What happens? How do I talk to my manager? How do I walk into a bank and say, hey, you know what? I'm going to break your system on purpose. The customer is going to freak out. Of course. Well, that's not how you talk to them. You tell them that I'm going to make your applications resilient. They will get it. They'll buy the dream. That's how you talk to them. Behind the scene, yes, you understand. A lot of it is psychological. A lot of it is, how do you talk to the customer? What is the end benefit, right? Now, when you talk to your colleagues, then you say, what resiliency, whatever. We're going to do chaos engineering. Your employees get excited. So really depending upon who you are talking to, that's sort of the approach that you go with, okay? So I think that's really the key part that you want to understand. It's all about making your system resilient. Now, Andy Grove, founding CEO of Intel, he says, only paranoids survive. And that's what this is about. So if you are not paranoid about your application breaking at 2 in the morning, there's something not right. So you really need to think about, how can my application break? What are the ways it can break? This is a quote by Nora Jones. She was part of the chaos engineering team. That team, by the way, is now called as the reliability engineering team. And she says, chaos doesn't cause problems. It only reveals them. Take an example. So let's say your service was supposed to talk to a caching service and then return the results back. What if your caching service is down? What do you do? Well, maybe the service should be able to ignore the cache in that sense, go back to the persistent layer, pull the data out. Not a suboptimal experience, but customer is not suffering. You're at least not throwing a 404 or a 500 server error to the customer. But at least you are identifying that's an issue. I'm a big Netflix user, so I watch Stranger Things. If you like Stranger Things, then I would recommend watching Typewriter. That's an Indian version of Stranger Things. Pretty cool, though. Now, one of the features in Netflix is I watch 30 minutes, somebody comes in, I get distracted, or flight lands down, then I have to watch it somewhere else. It's a bookmarking capability. So where I can resume the video at a later point of time. What if that bookmarking service is down? What is the optimal experience? Because end of the day, if you think about the Netflix architecture, there's a bunch of microservices sitting behind. So if that bookmarking service is down, then I should not tell the user that, I'm sorry, I completely lost it. I don't know what you were watching. You should be able to at least resume back from the beginning. Tell the customer that. And then at least you have identified a weakness in your system, and that's what you need to fix, essentially. So how do you start, really? I'm not, as I said earlier, I'm not talking about unit test failures, system failure, integration failures. This is really where you start small, you inject failures in your system one by one and all over the place. What if my Kubernetes cluster not able to scale? I'm running, I'm not running horizontal pod autoscaler, I'm not running cluster autoscaler, for example, and all of a sudden my pods are not able to serve the requests. What happens then? What if I'm running a virtual machine, out of 10 virtual machines, 5 come down? Bunch of scenarios that can happen. And so that's what you need to think about, really. What if the number of concurrent users become 10,000 as opposed to 100? How is the app going to behave? Is it going to jam completely? Is it going to freeze? Is it going to die? Is it going to become a brick? So where do you inject chaos? Literally anywhere across the system. Application, your caching layer, your database layer, your cloud layer. There are capabilities, for example, if you look at Gremlin, that's the thing that Colton and I were talking about, how you can have a zone, you can mimic a zone failure. That, hey, my application is running across multiple zones or multiple regions. I want to mimic a zone failure or a region failure. How would my application behave in that? Are you really running? We have at AWS, we have this well-architected framework which we expect customers to run. And that gives you guidance in terms of, is your application highly available? Is it resilient? Are you following the best practices for building those highly available applications? So let's get into more details about phases of chaos engineering. What is this about? So this is basically about, you want to address the uncertainty of distributed systems at scale. To an engineering mind, that uncertainty is like, oh, how do I handle that? And I want to control, I'm an engineer, I want to freaking control everything. But then that's the reality of a system, okay? So essentially, it's a set of experiments that you need to identify, and you make them run through different phases. You define a steady state, you define what a hypothesis is, you design the experiment, you verify and learn. Those are your 4 primary stages. And then once you have done all of those stages, then you essentially figure out how I'm going to fix it, if I need to fix it, if there are weaknesses identified, okay? Let's go through them one by one. So the first one is really a steady state, which is some measurable state output of a system that indicates normal behavior, okay? For example, in this case, this is sort of the normal behavior of your service, that I have crests, I have troughs, and I can manage them over a period of time. I know exactly how it looks like. So if you need to set up your auto-scaling groups, you can set them up accordingly. You start defining a metric around throughput, latency percentiles, error rates, all of those. So you're not really thinking about, oh, how my CPU is doing or how my memory utilization is doing. It's not about that. It's really about a more holistic system-wide metric, as opposed to, CPU and memory, of course, will impact the system, but those are not really visible to the user. You're really talking about, can I serve 10,000 concurrent users and serving a page in less than a second? That's the kind of metric you define. So let me give a more concrete example. So Netflix, this is a beautiful blog that they wrote a few years ago. They talked about how they identified a top-level metric. It's called as SPS, or starts per second. And essentially in that, what they're saying is that we're going to track how many starts are happening per second. And this is a server-side metric. So they basically are a lot of discussion, a lot of debate, but ultimately they ended up with that one metric to begin with. Now, this metric is a lot of things for them. This basically helps them identify, because that is their primary business, right? The primary business is customers viewing, and if they're able to start that many streams on the back end, if the back end is scaling or not scaling. So I would highly recommend take a look at this. Now, in this, they started looking at it. Starts per second could be different for different geographies. It could be regional. There's a holiday in US, there's a holiday in Europe. What is the weekend time? So they started maintaining these starts per second across different geographies, across different regions, and then they closely started monitoring the patterns. And then the moment starts per second, based upon the trend that they have, falls below a certain threshold, they know something, there is a problem in there. And then everybody is tied in. So the more closely your experiment and the metrics are tied, the easier it is to then kind of make an impact on that. So the next step is, once you have identified what your steady state is, a hypothesis. Hypothesis is what if? What if network fails? What if my system crashes? So what you do is you define sort of a control group, which is a bigger group, which is not impacted, which is running as it is. And then you define an experiment group. Experiment group is a much smaller subset of the control group, because that's where you're going to induce your experiments, for example. Okay? And then you start looking at your what if analysis. What if a service gives a 404? Not available, whatever reason. These are some of the what if scenarios that can happen. What if somebody accidentally changed the security group? What if the IAM credentials are somehow changed and they're not letting me access my service at the back end? What if IP tables are wiped out? Really, go wacky completely. See, as crazy as you can go, because those things can happen in the real world. So that's the way you really want to simulate this and see how your system is going to behave for that. So once your hypothesis is defined, then what you need to do is you need to simulate it. And that's exactly what you are designing the experiment stages. So you have picked your hypothesis, you have scoped the experiment, that, okay, this is what my scope is going to be. I'm going to be targeting this experiment to 1% of the users using a certain user agent in a certain geography at 11 in the morning. So really make it down narrow so that the impact is not highly visible, but you're still testing in production. You don't want to see a tweet, somebody complaining about your service. Oh, that service sucks, it's down. You don't want to do this Friday evening, 8 p.m. Pacific time, where everybody is jumping on and saying, what, I'm going to do shopping or watch some streaming service. So think about the time and think about the impact that it's going to have. So you start really small, you run it in production, that's the key part here. Identify the metrics. How are you going to tie those metrics to your backend? And the important part really is you have to spread that message across the organization. A really key part over here is who owns that responsibility. Because unless the organization is prepared that, hey, we are running a game day here, nobody would be expecting this. So give a heads up. Because if you give a heads up, the organization is prepared. And if there are, have an emergency stop button, for example, if the experiments go bad, if it just starts to percolate all over the place. So have that emergency stop button where you can say, okay, I'm not done with the experiment. I learned a few things. Let me fix those, and I will revisit that experiment. So this is a typical example that how you can scope the experiment. One of the features in Route 53 is where you can switch between, two different set of virtual machines. So you could say, I'm just going to start with 1% of my users. So very common way, canary deployment. See if the canary comes back, it's good, then you expand. If the canary dies, experiment is successful, you learn something about your machine or your system, and then you move on with that. So now you have had the steady state, you've done the hypothesis, you've designed the experiment. Now we get to the verify and learn stage. So this is where you talk about MTTF, mean time to failure. You talk about MTBF, mean time between failure. You talk about MTTR, mean time to recovery. Those are some of the aspects that you think about, in this quantifying the result of experiment. So hopefully, you have identified a problem, the systemic problem that needs to be fixed and updated. This is where you need to understand how long does it take to detect a failure. And once you have detected the failure, how long does it take to recovery? Is it a self-healing system, as a matter of fact? Or is this something that you have to build in your application so that it becomes self-healing? And those are the kind of concepts that you really look at. So in our previous example, for example, if the caching service goes down and the service starts responding back badly, that's not a good customer experience. So you really want to think about, what is my graceful degradation path? And I was watching Netflix streaming once, and then I saw that it was a HD video, and then from HD, it falls down to non-HD video. And then a couple of minutes later, it went back to HD. That's a super cool experience. Because now there was a graceful degradation, probably something happened in the background, and then it just went back to HD. So how do they do that in the background without a customer impact? No, it's amazing. It's very important to not blame that person who caused the bug. One of my managers, she taught me this lesson, which really I took to my heart. We generally find an issue, and you become warm with the issue, and you become cold with the person that you caused the bug, and goes on forever, right? As opposed to think about the issue. Let's become cold with the issue. Now, everybody makes mistakes. Let's become cold with the issue and say warm with the person. At KubeCon Barcelona, somebody was there from Spotify. He was giving a keynote, how I broke my Kubernetes clusters twice, and it was a production outage. So think about that use case. Think about the Spotify culture, that they are encouraging people who are breaking their clusters to now go give a keynote talk about it. I don't know how many companies will oh shoot, you broke the cluster, fired. So let's hope that's not the culture that we're building, because we need to tell our generation and younger generation to be able to fail and recover from it. Those failure lessons are super important. At Amazon, for example, we have this concept of a correction of errors. Anytime a severity 1 incident happens, we look at correction of errors. And in the correction of errors, the whole concept is what happened, why did it happen, what was the root cause. It's never about the person at all. It's very explicit focus to not be about the purpose. What corrective actions you learn from it. So let me walk through a made up correction of error process. In that, basically what we talk about is the 5 whys, okay? So the outage happened, for example, and customers were not able to access, say, the service for 45 minutes. Okay, why did that happen? Well, because there was an unprecedented demand from the service. So why there was an unprecedented demand? Well, because our service was dependent on another service that could not handle the demands. It was not our service, but somebody else's service, okay? Well, the service that we depended upon did not meet the SLA, okay? Then the service did not meet the SLA because there was not enough capacity. So you just keep going, you just keep peeling the onion, and then we figured out, oh, by the way, in between steps were irrelevant. What really matters is there was no graceful degradation path. And as I said earlier, it's never about the people, it's about the process. And I've been involved in a correction of error once, so I won't say what it was, but it was a delightful experience to see how do you have to go through this. And it's never about the person, it's about the process, so that you document it, it doesn't happen again. And that's what makes your applications a lot more resilient. So now, you have run the experiments, all of that has happened. So after running your experiments, let's say you identified 2 things. First is, hey, everything looks good. I pulled the plug on my VMs, I broke the containers, I killed my DNS service, everything worked, awesome. Doesn't happen all the time, and doesn't happen any time at all actually in real life. So now the part is where you have learned some things about your system, and then you have to go and implement them in the system. That, okay, how do I make this? And you better fix it, because that's what is going to happen in your real life otherwise, okay? So here, Rich Cook wrote a beautiful paper on how complex systems fail, okay? And I love this quote. It says, failure-free operations require experience with failure. How many of you have participated in fire drill at your work? Pretty much all of you, right? We hate it. It's like, dang, I was right in the middle of a meeting and they're ringing their alarm, is deafening me. But we need to be ready for it. If it happens in real life, hopefully it's not a popcorn, but if it's a real thing, we need to be ready for it. So I think that's sort of what the essence of this is. So with chaos engineering, you're breaking your systems in purpose and be ready to face it, so that if this thing happens in real life, you're able to recover gracefully from it. You want to learn more about chaos engineering? This is a beautiful mind map. It's a lot confined here, but take a look at this URL, and I will share my slides as well. But here it talks about the entire mind map. It talks about companies, people, tools, practices, anything and everything around it. And as I said earlier, September 27th is Chaos Conf. So if you guys are interested, that's where all of the mind of chaos engineering are meeting together. So definitely worth a look. I'm going to conclude with this last quote by Mike Birch. We're close to Palo Alto. So this was given by the fire chief of Palo Alto. He says, you don't choose the moment chooses you. When this outage is going to happen, you don't know. You hope it doesn't, but it does. And then it's all about how prepared you are when this moment happens. So chaos engineering, if you think about it, is in addition to your usual system testing, integration testing, unit testing, it builds on top of that, where it finds system problems at scale, particularly for distributed systems. Whether you're using microservices, whether you're using VMs, whether you're using containers, it can apply to whatever you're doing. And that's sort of the essence of chaos engineering. Thank you. So I'm going to be around for next hour or so and would love to talk to each one of you. Thank you.